next topic we are going to learn about is the topic of combinations. We have learned about permutation. When we talked about permutation, remember we were focusing on the word ordered arrangement. Okay. So, now let us go and understand what is a combination. So, let us start with an example. Suppose I am asked to select, I am clearly telling I want to only select 2 students from a group of 3 students. Here we are not emphasizing on any arrangement or any order. We are very clearly specifying that we only want to select 2 students or choose 2 students. I am not bothered about whether the first student or second student. I do not have any order here. So, in this case, let me start by telling that let me have A, B, C as the 3 students. Okay, just I am assuming that the first student is called A, B and C. Now, from these 3 students, if I have to make groups of 2, I can either have AB as a group, I could have AC as a group, or I could have BC as a group. I can see that I have 1, 2, 3. So, there are 3 ways of selecting 2 students from the group of 3 students. Okay. So, now this is AB, AC and AC. So, now here what you have to clearly understand is whether I write AB or BA is of no difference to me, because the order in it I could choose A first and B first, or B first and A first, or both of them simultaneously. There is no order in a combination. But when we talked about permutation, whether A occupied the first block and B occupied the second, or B occupied the first and A occupied the second, there was a difference. So, you can see that when I am talking about combination, the order is of no relevance to me. I do not have any importance to the order. Okay. Order is not important. That is something which you need to understand. So, now each selection, so I have 3 selections, my selections are AB, AC and BC. Each selection is called a combination. That is what we have written here. So, in general here I had 3 objects and I selected 2 from this. So, I have from 3 I am selecting 2. In general, if I have n objects and I want to select R objects, I say I am choosing R from n or selecting R objects from n objects, or I am choosing at a time, choosing R objects from n objects at a time. Okay. So, now going back to the example, I have, suppose I am looking at the possible combinations taking 2 at a time. When we went back to our permutation, we had a first place and a second place. Here it really does not, the order is of no importance here. So, when I had the permutation, my first place could be an A or a B, or it could be a B or a. The first place could be an A, or a second place could be a C, or it could be the first place is a C and my second place is an A. First place is a B or a C, or my second place is a C or a B. These were the possible ways I could have had. So, you can see that if I have a AB combination, this has 2 arrangements. One is A in my first place, this is my second place, and B in my second place, or B in my first place and A in my second place. AC combination or AC selection, I could have an A in my first place and C in my second place, or C in my first place and A in my second place. BC combination could have a B in my first place, C in my second place, or C in my first place and B in my second place. Recall the number of permutations of two objects from 3, which was 3p2 was 3 factorial into 3 minus 2 factorial, which was nothing but your 6. I have 1, 2, 3, 4, 5 and 6 possible permutations. The number of combination is 1, 2, 3. So, from this example I have that the number of combinations which is equal to 3. Each combination is giving rise to 2 permutation or 2 factorial permutation is giving me the number of permutations. I repeat, the number of combinations which is 3, each one is giving rise to 2 factorial or 2 permutations. So, finally, I have the number of permutation which is 6. So, number of combinations into 2 factorial is giving me the number of permutations which was 6. I can extend this logic to n things. So, if I have n objects and I am choosing R from these n objects, then I can say that if I have my first combination of n objects from R objects, each of these R objects can be, so the one combination would give rise to R factorial arrangements. Okay. The second combination will also give rise to R factorial arrangement. So, every combination gives rise to R factorial arrangements. Now, why is this important to us? From this, we can actually set up what we are referring to as a combination notation and formula. So, in general, each combination of R objects from n objects give rise to R factorial arrangements. That is what I have the, if I have one combination, then afterwards it will give rise to R factorial. The second combination, another R factorial arrangements. Okay. So, if I am going to denote the number of possible combinations of R objects from a collection of n distinct objects, I repeat, the number of possible combinations of R objects from a collection of n distinct objects is denoted by n choose R. I am choosing R from n distinct objects. So, this is the number of combinations. If I have from one combination, I am going to have R factorial permutations. So, from n choose R, I am going to have n choose R into R factorial arrangements. Now, this n choose R into R factorial is nothing but the total number of permutations, total number of permutation. This is what we saw in our example. Okay. So, in general, what do I have? I can write this n choose R into R factorial is NPR. Again, I repeat, from one combination I get R factorial permutation. So, each combination, because I have R objects, these R objects among themselves can be arranged in R factorial ways. If I have 2, I will have 2 into R factorial. N choose R is the total number of combinations. So, N choose R into R factorial is going to give me the total number of permutations possible. I already know NPR is n factorial by n minus R factorial. So, I have n choose R into R factorial is n factorial by n minus R factorial to give me the formula n choose R is n factorial by R factorial into n minus r factorial. Okay. So, this is the formula for n choose r, and the way I express it is the number of possible combinations of r objects from n distinct objects. Okay. So, in the earlier example, I chose 2 objects from 3 distinct objects. So, it is 3C2. Applying the formula, it is 3 factorial, which is n factorial. R factorial is 2 factorial. 3 minus 2 factorial is a 1 factorial, and I can see that this is equal to 3, which actually is the total number of combinations which I got, namely AB, AC and BC. I had 3 combinations. So, this formula is the number of possible combinations of R objects from n distinct objects. Another common notation which is used by many authors and book is n choose r. This is also referred to as a binomial coefficient. Some of the books use this. Either of these notations are fine, n choose r or n choose r. This is referred to also as a binomial coefficient. Some useful identities, combinatorial identities, which will be useful for us to understand more about the combinatorial formula. The first thing is n choose r. So, if I start with the n choose r, by my formula I have this is n factorial by r factorial into n minus r factorial. Now, in the denominator I can write it as n factorial by n minus r factorial into r factorial. These two are equivalent. I am just changing the order in which I have written them. So, what do I get now? Now, this, if I am applying the same formula, this is same as n choose n minus r. So, the first identity we have is n choose r is equal to n choose n minus r. In other words, what we mean is selecting n choose r, I can express as selecting r objects from n objects. N choose n minus r is same as rejecting n minus r objects from r objects. So, if I have n objects or n people, if I select r of them, I am basically rejecting n minus r of them. So, if I have some ways of selecting these r objects is equivalent to rejecting these n minus r of them, and that can be established by this identity. The next important identity which we have is n choose n. Again, applying the formula, I have n choose n as n factorial by n factorial into n minus n factorial. I have which is same as n factorial by n factorial into 0 factorial. Recall 0 factorial is equal to 1. So, I have n choose n equal to 1. Now, when we look at NC0, we can apply the earlier identity. I know n choose 0 is same as n choose n minus 0, which is equal to n choose n. I have already established n choose n equal to 1. So, n choose 0 is also equal to 1. I can prove this from first principle. Again, n choose 0 is n factorial by 0 factorial into n minus 0 factorial, which is n factorial by n factorial. Again, 0 factorial is 1, which is equal to 1. So, these are two important combinatorial identities that we need to understand. Now, the third identity n choose r equal to n minus 1 choose r minus 1 plus n minus 1 choose r. This is a very important and a useful combinatorial identity. I am not going to formally prove this, this can be proven, you can give a proof for this also, but let me give you the intuition behind this identity by using an example. For example, if n equal to 5 objects and I have to choose 3 objects out of them. So, let me assume that I have A, B, C, D and E who are my 5 students or 5 people or my 5 objects, and I have to choose 3 from them. Okay. So, now I choose one of them. For example, if I choose A, okay, I am choosing A. So, there are two ways of looking at my total choices. One way is that the 3 group, that is the group of 3 has A in it, and the second is A is not a part of the 3 that is chosen. One way is A is a part of the 3 that is chosen, and A is not a part of the 3 that is chosen. Now, if A is a part of the 3, so I am choosing 3 objects. If A is a part of the 3 that is chosen, I have to choose remaining 2. If A has already been chosen, I have to choose the remaining 2. For the remaining 2, if A is chosen, I have 1, 2, 3, 4 available with me, and I have to choose 2, and I can do that in 4 choose 2 ways. Because A is already chosen, I only have to choose 2 more objects. I have a remaining 4 objects to choose that from, and that I can do in 4 choose 2 ways. Now, suppose A is not a part of the 3 objects. Then in that case, I have 4 objects available with me, which is B, C, D, E, and I have to choose all the 3 objects from this choice of 4 objects, and that I can do in 4 choose 3 ways. So, the total number of ways I can choose 3 from this choice of A, B, C, D, E, which is 5 choose 3, is equal to 4 choose 2 plus 4 choose 3. So you can see that n equal to 5, r equal to 3, n minus 1 is 4, r minus 1 is 2 plus n minus 1 is 4, r is 3. So, this is what we have got in this example. In general, if I have n objects and I have to choose r from these n objects, I can fix. So, the way I can understand this is I fix any one of the n objects. I fix any one of the n objects and I look at the situation that the r objects has n and r does not have n. If r has n, since I have already chosen one of the n r objects, I only have to choose r minus 1 of the objects from remaining n minus 1 objects. Here r does not have n, I have only remaining n minus 1 because I am eliminating n, I choose r, and these two put together give me n choose r. I use this n minus 1 choose r minus 1 n minus 1 choose r, and this is n choose r. So, this is an important combinatorial identity which we can use or apply, and we will be applying such identities whenever we go to the application aspect. So, now let us look at a few examples to apply the concepts of combination we have learned so far. One is choosing questions in an exam. So, consider a situation where a paper consists of 12 questions. Now, these 12 questions are in two parts, part 1 and part 2. Part 1 has 7 questions, part 2 has 5 questions. So, 7 plus 5 is 12 questions. Now, a student has to attempt 8 questions in all. How many questions should a student attempt? A student has to attempt 8 questions. So, the condition is he has to choose at least 3 from each part. So, I have a part 1, I have a part 2. I can either choose 3 from here. If I choose 3 from part 1, I have to choose 5 from part 2. If I choose 4 from part 1, I have to choose 4 from part 2. If I choose 5 from part 1, I have to choose 3 from part 2. I cannot be choosing 6 and 2 because this would be violating the at least 3 from each part. So, if it is at least 3 from each part, these are the possible ways I can choose these 8 questions, assuming that the student is choosing exactly 8 questions out of the 12 questions. Now, how many ways can this be done? The number of ways this can be done is, I have 7 questions in part 1. The number of ways I can choose 3 questions from 7 questions is 7 choose 3. The number of ways I can choose 5 questions from 5 questions is 5 choose 5. So, I have a 7 choose 3 into 5 choose 5 is a total number of ways I can choose 3 from part 1 and 5 from part 2. The number of ways I can do this is 7 choose 4 into 5 choose 4. Number of ways this can be done is 7 choose 5 into 5 choose 3. So, the total number of ways a student can select questions is 7 choose 3 into 5 choose 5 plus 7 choose 4 into 5 choose 4 plus 7 choose 5 into 5 choose 3, which I can see is equal to 35, because 7 choose 5 into 5 choose 5 is 7 factorial by 3 factorial into 4 factorial. 5 choose 5 is 5 factorial by 5 factorial into 0 factorial. So, this is equal to 1. 7 factorial by 4 factorial, 3 factorial into 5 factorial by 4 factorial into 1 factorial, 5 factorial into 2 factorial into 5 factorial by 3 factorial into 2 factorial. So, this is equal to 1. So, this is 7 factorial into 35. So, 7 into 5 I have a 35. Similarly, here I will get a 5. So, from here I have a 7 into, this is again a 35. Here I have a 7 into 3, which is 21, into 5 factorial into 4, 5 into 2, which is a 10. So, this in total gives me, this is 175. So, I get a 35 plus 175 plus 210, which gives me a total answer of 420. So, now let us introduce you to a game of cards. The reason why I am introducing you to a game of cards is, when you look at problems in probability, there are a lot of problems in probability which are based on a game of cards. So, I will just introduce you to a game of cards. It is no gambling here, we are just, it is a nice way to understand the concept of probability. That is why I am just introducing you to a formal deck of what we refer to as playing cards. Now, when you look at playing cards, these are called as suits. So, I have clubs. A club is something of this kind. This is what I refer to as a club. Then I have what I refer to as a spade. Then we have hearts. And we have diamonds. A typical pack of cards has clubs, spade, hearts and this is a diamond. So, now let me introduce you to a pack of cards. We are introducing you to a pack of cards because of many problems in probability from many textbooks, and whenever you learn probability, you will be introduced to questions which require you to understand something about a pack of cards. So, when we look at a pack of cards, we have clubs, we have spade, we have hearts and we have diamond. Now, these are referred to as suits. So, typically I have 4 suits, and what are the suits? They are clubs, they are spade, hearts and diamond. Each of them have 13 denominations, that is I have A, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 denominations with 4 suits, which will give me a total of 52 cards, and typically I will have of these 52, 26 are black and 26 are red. This is how a pack of cards is typically given to us. Now, suppose I have to choose 4 cards from these 52 cards. I am not placing any other condition, I am just telling choose 4 cards from this 52 cards. How many ways can we do it? The answer is pretty simple. It is just 52 choose 4, because I am not qualifying that what is it I require. I am not saying choose 4 red cards, I am not choosing choose 4 clubs, I am not saying choose 4 spades, I am just telling choose any 4 cards, and those 4 cards could be a 2 clubs or a 3 spades or a 5 hearts or a 7 diamond. This is a perfect choice where I have chosen these 4 cards. And how many ways can we choose 4 cards from 52 cards? The ways I can choose 4 cards from 52 cards is just 52 choose 4, which is equal to this number, which is a pretty large number. Now, suppose I am telling that all the 4 cards are of the same suit. So, let us go back here. Earlier I said that let us choose a 2 clubs, 3 spade, 5 hearts and 7 diamond. You can see that all these 4 cards are of different suits. I do not want this. This is not an acceptable selection for me. What is an acceptable selection? If I had a 2 clubs, 3 clubs, 6 clubs and 7 clubs, this is acceptable to me. 2 diamonds, 7 diamond, 10 diamond and a queen diamond, this is also acceptable to me. But a 2 hearts, a 3 hearts, a 4 diamond and a 5 diamond, it is not acceptable to me. So, how many ways can I choose this? Again, the requirement is choose 4 cards, but they should be of the same suit. So, the way we can do it is, first let me choose a suit. How many ways can I do it? How many types of this? How many suits are there? There are 4. I need to choose 1 out of the 4, and how many ways can I do that? I can do that in 4 choose 1 way. Now, within each suits, I have 13 of each kind, and I need to choose 4 from these 13, and that can be done in 13 choose 4 ways. So, the total number of ways I can choose all the 4 cards from the same suits is 4C1 into 13C4, which is equal to 2860 ways of doing it. Now, let us go to another problem. Now, I am asking how do you choose the cards of the same color? Now, again go back. How many colors do we have? You can see that we have 2 colors, how many ways can I choose one color from 2 colors? Again, the number of ways of choosing one color from 2 color is 2, choose 1. Now, within each color I have 26 cards, that is what we have seen, and I need to choose 4 from each color. So, I can do that in 26, choose 4 ways. So, the total number of ways I can choose 4 cards of the same color are 2 choose 1 into 26 choose 4, which we can see is 29,900 ways of doing it. Okay. So, let us move on to the next example. Now, suppose all of us know how we choose cricket team. A cricket team has 11 players. Of these 11 players, we need to have some players who are batsmen, some who are all-rounders. We need a wicket keeper. We also need bowlers. Suppose I have 17 players available with me. I have 17 players available with me. Of these 17 players, only 5 players can bowl. So, I have total 17. So, recall I can put it in the framework of my question paper. Of these 17 question players, I have 5 who can bowl. So, 17 minus 5 is 12 who cannot bowl. Okay. I need to choose 11 players. The requirement is it should have exactly 4 bowlers. So, if it should, the requirement is it should have exactly 4 players. I am not saying at least, I am saying exactly 4 players. If I have 4 bowlers, then I should have 7 non-bowlers in my team to make up to the 11 players. How many ways can the selection be done? The 4 bowlers can be chosen from the 5 bowlers in 5C4 ways, which leaves 12C7 to be the number of ways I can choose the 7 remaining players from the 12 players to give me a total of 5C4 and 12C7 to give me a total number of ways as 5C4 into 12C7, which I can simplify as 5 into 792, which is actually 3,960 ways of selecting my team. Here the qualifier was I should include exactly 4 bowlers, and I can choose these 4 bowlers from 5 bowlers and the remaining 7 players from the remaining 12 non-bowlers. So, this is how I can have my team selection and apply the combinatorial or combination formula which we have stated earlier. Now, let us look at another example. Suppose I am given n points in a circle. The question is how many lines can be drawn connecting these points. So, now let us look at a very simple case of n equal to 2. Let me term the points A and B. So, given A and B, I know I can draw only one line connecting A and B. So, you can see that I am referring to that line segment as A, B. Given 2 points on the circle, so n equal to 2, I can connect it only with 2 points. Okay? Sorry, given 2 points, I can connect it using one line. Suppose I am given 3 points. Okay? So, now you can see that I have A, B and C are the 3 points. I can connect AB with a line segment. I refer to that line segment as AB. I can connect AC with a line segment. I can also connect BC with a line segment. So, I can refer to my line segments as AB, AC and BC. So, I am given 3 points. What are the 3 points? My 3 points are, so in the, when n equal to 2, I had points A and B. My line segment was AB. I had one line. When I had points A, B and C, I could form segments AB, AC and BC. So, I have 3 line segments. So, immediately you can notice that if I have to draw a line segment, I need 2 points. I have 3 out of 3 points. I can select 2 points at a time in 3 choose 2 ways, and that 3 choose 2, we have already seen 3 choose 2 is equal to 3 factorial by 2 factorial into 1 factorial, which is 3. So, I have 3 lines 1, 2 and 3. Here 2 choose 2 is 2 factorial by 2 factorial into 0 factorial, which is 1, and hence I have that number which is equal to 1. So, in general, if I am given n points, if I have n points on the circle, to draw lines, I need to choose any 2 points. That is, if I fix this point, I can draw lines between any 2 of these points. Given n points, I can choose these points in n choose 2 ways. So, the number of line segments that can be drawn connecting the n points is n choose 2. Again, here there is no direction in this line, I just have a line which is AB. The order is not important because whether I refer to BA or AB, it is the same here. So, I am looking at a combination. So, in summary, we have started, or we gave what is the notation and formula for selecting R objects from N objects. We represented that by N choose R, some books represented by N choose R, the binomial coefficient. We saw N choose R is given by N factorial by R factorial into N minus R factorial. This is the important combinatorial formula which we gave, and then we gave some useful combinatorial identities. We described them and qualified it, and we also gave a few applications of combinations. That is what we have done in this section.